So again, Greek letter sigma, sigma notation, also called summation notation. It's used to add a bunch of numbers together. Okay, and that's all that we'll be doing with it. Okay, we'll be using this to add a series of numbers together. Okay, so we're going to take 5, 6, 7 numbers and we'll add them together to get our answer. And this is kind of the shorthand way to represent a bunch of numbers that we're adding together. And I'll show you here with an example. Okay. So here's what a very simple problem might look like. Okay. You'll see the Greek letter sigma. You'll see a starting number at the bottom. Most of the time it's 1. Doesn't have to be. But most of the time they'll start with the number 1 down here. So this is like your starting number. And the number on top is your finishing number, or your last number. Okay? And then you'll have a rule. And this rule is where you'll plug in the numbers that it's telling you to. Okay? Yes?
The number on top, is that like the last term or the value of the last term?
That is the last value of n you will substitute into the rule. So what's going to happen here, if you see this, the first thing you're going to do is plug in a 1 for n and write down the number you get. So 3 times 1 is 3, minus 1 is 2. So I write down the number 2. This is the first number that I'm substituting in for n. Then I plugged in a 1 for n and I got 2. Now I'm going to plug in a 2 for n. 3 times 2 is 6, minus 1 is 5. So that's the next number I'm going to add. And I'm just going to add all of these numbers together. So now I'm going to plug in a 3 for n. 3 times 3 is 9, minus 1 is 8. So that's my next number. Now most of you are going to recognize the pattern, which I would expect, but in case you don't, let's plug in a 4 for n. You get 11. Plug in a 5 for n. You get 14. Plug in a 6 for n, and you get 17. Okay? And now I'm done. I'm just going to stop there. I'm not going to plug any more numbers in for n because it told me to stop once I get to 6. So the number down here tells you the first number to substitute in for n. And then you keep substituting in every number above it, counting by whole numbers obviously, until you get to the number on top. And then you just take a calculator and add them all together, although I will show you shortcuts for longer problems here shortly. Okay? So add them all up, 7, 15, 26, 40, 57. The answer would be 57. So the answer to this is 57. Okay? All this is telling you to do, it's telling you to find the sum, or add up all the numbers, 3n minus 1, from where n equals 1 through 6. Is basically what it's telling you to do. Okay? Questions? This is new notation. There are not stupid questions here. Alright? Try this one yourself. Right?
So wait, do you start at 3 then?
Yes. Yep. So 3 will be the first number you will substitute in for n. Now most of the time, it is going to start at 1. Okay, but I just wanted to use a different number to show you that it doesn't have to.
Okay.
Alright? But most of the ones you do, especially the ones you write, you'll see start at 1. So when you substitute in a 3, what do you get? 8, good. Substitute in a 4, what do you get? 16. Substitute in a 5, 32. At this point, you recognize the pattern. Doubling, right? So I plugged in a 3, I plugged in a 4, I plugged in a 5, so that means when I plug in a 6, I must get 64. When I plug in a 7, I must get 128. When I plug in an 8, I must get 256. Do I need to keep going? Nope, because it said the last number you need to plug in has to be that number on top of the sigma. And then just add them all together. Anybody done it yet?
I did that wrong.
504.
I got huge numbers.
Probably because you were multiplying 4 times 2 together before raising it to a power.
I just put 8 in parentheses, raised to...
It's 2 raised to this power times 4. Exponents come before multiplication.
Yeah. That's 262.
Okay?
Does it get harder than that?
I got an 8.
Really? Other questions? So, I could give you this sigma notation here, and when I give that to you, I'm asking you to add up all those numbers and give me one answer. Okay? The other thing you will have to do a little bit, and this will just kind of go back to what we've done before with the writing of the rules, but I might give you the numbers to add together, and you need to write sigma notation, so the exact opposite. And it's not difficult. You're very capable of this. Okay? If you need to write the sigma notation for adding those numbers together, do yourself a favor and start with your first number being 1, right? Well, if the first number we plug in is 1, what do you think the last number we plug in is going to be? 5. Why?
It's 5.
Because you're adding together how many numbers? 5 of them. Now the only thing left is to figure out what rule to substitute those numbers into. Well, what type of sequence of numbers is this? Arithmetic. So can't we write the rule?
Yeah.
So a sub n equals a sub 1 plus d times n minus 1, right? So a sub n equals first term, 13, common difference, 4. So 13 plus 4 times n minus 1, and you simplify that, you get 4n plus 9. There's your rule. And then you could double check to make sure you're right. If you plug in a 1 for n, do you get 13? Yes. If you plug in a 2 for n, do you get 17? Yes. Plug in a 3 for n, do you get 21? Yes. Plug in a 5 for n, do you get 29? Yes. Okay. So that's the other way I could go with this. I could give you the numbers we're adding together and ask you instead of to write it as sigma notation or summation notation.
When you're writing it, would you always have n equals 1?
No.
Okay.
Yes, I probably would, but no, you don't have to.
Okay.
Okay? Give me a different number. Besides 1. 4, okay. So if you want the first number for me to plug in be a 4, 4, 5, 6, 7, 8, so I know then that 8 has to be my last number. Alright. And because the pattern is adding by 4 at some point, I know I'm going to have a 4n in my rule. But if the first number I'm plugging in is 4, 4 times 4 is 16, I know it has to equal 13. Well, 16 minus what is 13? How about minus 3? This, and this, and this, they're all the same. You plug in a 4, you get 13. You plug in a 5, you get 17. You plug in a 6, you'll get 21, and so on. So this would be a correct answer too. Most people aren't going to do that. But this is exactly saying the exact same thing as this. To me, it's easier to just start it at 1, but you don't have to. Because if you start it at 1, you can use the arithmetic rule that hopefully you practice in the first part of this chapter. But yeah, somebody made me use 1,400 and something as my first in value here in 4th hour, and I showed them how it can still work. Okay. All right? So, sigma notation. Questions so far?
Without her just like telling your full analogy, you can find this.
Well, what I'm saying is you can use any number you want to. I wouldn't if I were you. I'd use 1 every time. But I'm saying you can use any number you want to. You'll have to adjust your rule then to make sure it matches, Luke. But all right, so would this one be fun?
No.
No, why not?
I have to go from 1 to 80.
There's so many.
There's so many numbers, right? So many opportunities for mistakes. How many numbers are you going to add together?
80.
80 of them, right? Because you have to plug in a 1, see what you get. Plug in a 2, see what you get. Plug in a 3, see what you get. And then eventually plug in an 80, see what you get, and add all those numbers together. Okay? I won't ask you to do that by hand. Okay? You'll get a little shortcut formula or a rule to get that done. Okay? Now, to show you how I'll figure out a quick way to do that, let me use a set of numbers that we're going to add together to come up with a shortcut to add them together, okay? Alright, pay attention to this. Let's say I was going to ask you to add all the numbers 1 through 100 together. Okay? 1 plus 2 plus 3 plus 4 plus 5 plus 6, 9900. Okay? Alright. A real quick way to do this with an arithmetic sequence, which that's what this is. This is arithmetic, right? Because what am I doing each time? Adding 1. I'm adding the same number. Okay, so as long as it's arithmetic, you can follow this little trick. Okay? If I take 1 plus 100, what do I get? 101. 2 plus 99. 3 plus 98. 4 plus 97. I'm going to keep getting 101, right? How many times will I get 101? 50. Because what will be the last 2 numbers that I add together? 50 and 51. 50 and 51 will be the last 2. So 1 plus 100, 2 plus 99, 3 plus 98, 4 plus 97, 5 plus 96, 50 plus 51. All of those add up to 101, right? And how many sets of 101 will I have if the very last set of numbers I'm adding together are 50 and 51? 50 of them. I'll have 50 sets of 101 that I'm adding together. Okay? 101, 101, 101, I'd have 50 of those. Well, instead of adding together 101 50 times, it would just be easier for me to take 101 times 50, right? Okay? And there's your answer. Alright? 5,050. That's what you get when you add the first 100 whole numbers together. Okay? Now, what will always work then, what you'll always be able to do, is you'll always be able to take the first number plus the last number, so 1 plus 100, and multiply that by half of how many numbers there are. Or in this case, 50, right? So if I take the first number plus the last number, and I multiply it by half of the number of numbers you're adding together. That will always work with an arithmetic sequence or series. Okay? Fire away with your questions. No questions? I'm kind of waiting.
Can you just like ask?
Yeah.
With the way the equation's set up, isn't it really 101 times 100 and then divided by 2?
Correct, but I was trying to relate it to what we did.
So is it the same thing?
Aren't multiplication and division kind of on the same level in PEMDAS? So if you take something times 100 and then divide it by 2, wouldn't it be just as fast to take it times 50? So like that. So let's use, instead of times 100 divided by 2, let's do times 10 divided by 2. You know, let's start with the number 6. What's 6 times 10 divided by 2? 30. Well, instead of taking 6 times 10 divided by 2, what if we just take 6 times 5? Just a little quicker, right?
Just distribute them by
Okay.
2, though.
What's that?
I just distribute them by 2.
You can, I guess. To me, I'd do my parentheses. PEMDAS, right? I would do what's in the parentheses first. To me, that's easier than distributing. I mean, you certainly can distribute. Okay. So if you want to add together the numbers in a finite arithmetic series, finite means it eventually does what? Ends, stops, okay? Which this one does. I mean, it takes 80 numbers before it stops, but eventually stops. If you want to add together the numbers in a finite arithmetic series, here's the rule that you can use to help you without actually you adding all 80 numbers together. N represents the number of numbers you're adding together, or the number of terms, however you want to write it. N represents the number of numbers you're adding together, or the number of terms you're adding together. A sub 1 represents the first term. A sub n then would represent the last term. So first term plus the last term times the number of terms divided by 2. Okay? It only works for a finite arithmetic series. Is this arithmetic? What type of equation is it? Linear or exponential? Linear. Are linear equations arithmetic? Yes. Okay? So yes, this is an arithmetic series.
If you are a student that applied for NHS, National Honor Society, please pick up a letter in the secondary office. NHS applicants, pick up a letter in the secondary office.
So the sum of these 80 numbers will equal, what's n going to be? 80, because that's how many numbers you're adding together. What's the first term of the series? How do I figure it out? Plug in 1, right? Plug in 1 for n, what do you get?
-2. I mean 2.
Positive 2, right?
That's what I meant.
So my first term is 2. How do I figure out my last term?
Plug in 80.
Plug in 80 for n. 80 times -3 is -240. -240 plus 5 would be -235. All over 2. So 2 plus -235 would be -233. -233 times 80 divided by 2, or in other words, -233 times 40, right? -9,320 is what those 80 numbers would add up to. So it's a real quick way to add together a bunch of numbers in a finite arithmetic series. Check the calendar for homework.